In the deep black of a moonless sky, there is a faint smear of light that has haunted human vision for centuries. To the untrained eye, it is nothing more than a delicate cloud, a ghost adrift among the constellations. Ancient Persian astronomers knew of it well. In the 10th century, the great polymath Abd al-Rahman al-Sufi recorded its presence in his Book of Fixed Stars, describing it as a small cloud in the constellation of Andromeda. To him, it was a curiosity, a wisp of brightness among countless points of fire. No one yet imagined that this ghostly patch was a city of 1 trillion suns, an island universe on a collision course with our own dot through the Middle Ages and into the Renaissance. Andromeda's presence was whispered in astronomical catalogs, a static curiosity in a static cosmos. But the invention of the telescope turned this smudge into something stranger. In 1612, the German astronomer Simon Marius gazed upon it through newly ground lenses. What he saw was still a cloudy oval, but he sensed its distinctiveness, calling it the nebula in Andromeda. To him and his contemporaries, nebula meant a cloud, an object within our own galaxy, perhaps a birthplace of stars, perhaps a mere accumulation of cosmic dust. The universe, as they knew it, ended at the edge of the Milky Way. For 3 centuries, the Andromeda Nebula sat as one among many in astronomical catalogs, mysterious, beautiful, but bounded by an invisible assumption that all things lay within the confines of our galaxy. The concept of galaxies as separate universes was not just unproven. It was unimagined. That assumption began to fracture in the early 20th century. New telescopes, colossal by the standards of their day, reached deeper into the night. The 100-inch Hooker telescope atop Mount Wilson Observatory became the most powerful eye humanity had ever built. And with it, a new chapter began, one that would transform the Andromeda Nebula from a distant cloud into a cosmic revelation. In 1920, the so-called Great Debate unfolded between 2 leading astronomers, Harlow Shapley and Heber Curtis. Shapley argued for a small universe in which the Milky Way contained all the stars and nebulae. Curtis believed the spiral nebulae, including Andromeda, were island universes, vast, separate galaxies far beyond our own. It was a battle fought not with rhetoric alone, but with the data available at the time, photographic plates, crude spectroscopic measurements, and the limits of early telescopic resolution. Both men were speaking into a fog of uncertainty. 2 years later, the fog began to lift. In 1923, Edwin Hubble, a man whose name would one day orbit the Earth, in the form of a space telescope, turned the Hooker telescope toward Andromeda. He sought out Cepheid variable stars, rare cosmic beacons whose rhythmic brightening and dimming reveal their true luminosity. By comparing their intrinsic brightness to their apparent brightness, Hubble could measure their distance with unprecedented accuracy. What he found shattered the Milky Way's monopoly on the universe. The Cepheids in Andromeda were far too faint to be nearby. They were not a few hundred light years away, but over 2 million. The Andromeda Nebula was not a nebula at all. It was a galaxy, an island of stars more massive than the Milky Way, drifting far beyond its borders. The universe had grown unimaginably larger in an instant. From that moment, Andromeda became a cosmic yardstick, a reference point for measuring the scale of all that lay beyond. If one galaxy could lie beyond our own, then billions could. The night sky was no longer a dome enclosing us, but an ocean scattered with other islands, each as vast as the one we called home. In the decades that followed, the image of Andromeda sharpened. The Mount Wilson photographs gave way to the Hubble Space Telescope's piercing clarity. No longer a blur, the spiral arms emerged in breathtaking detail. Arcs of blue star clusters, lanes of dark interstellar dust, and the glowing core, bright with the combined light of billions of ancient suns. Infrared instruments revealed cooler, hidden structures. X-ray telescopes uncovered high-energy processes near its central supermassive black hole. With the launch of the James Webb Space Telescope, Andromeda's heart is now being examined in wavelengths unseen by human eyes. Webb's instruments have begun to peer through its dusty lanes, exposing pockets of star formation and unraveling the histories of stellar populations that predate our own galaxy. Each image is not merely a photograph, but a history, a frozen moment in a journey of light that began 2.5 million years ago. The Andromeda we see tonight is not the Andromeda that exists now. Its light has been traveling toward us since early humans first walked the Earth. The photon-striking modern detectors began their journey when our planet was locked in an ice age, when our ancestors hunted beneath a different set of constellations. In studying Andromeda, we are peering not just across distance, but across time itself. It is here, in this paradox, of something so vast, so old, so near and yet so far, that the true mystery of Andromeda's discovery lies. It was not merely the charting of a new place in the cosmos. It was the tearing away of a veil, the recognition that our home is but one among many. The smudge of light that Al-Sufi called a cloud became the first signpost pointing beyond the Milky Way, the first whisper that the universe is larger, stranger, and more ancient than we ever dared to dream. The revelation that Andromeda was not a cloud within our own galaxy, but a vast star city far beyond it, did more than double the known size of the cosmos. It dismantled the very architecture of humanity's cosmic understanding. In the aftermath of Hubble's 1923 measurements, a quiet but irreversible shift began. The Milky Way was no longer the universe. It was just one island in a boundless archipelago. The numbers themselves were staggering. Andromeda was not a few hundred or even a few thousand light years away. It was over 2 million. The faint smudge seen by Al-Sufi and Marius was, in truth, a sprawling spiral more than 220,000 light years across, nearly twice the width of the Milky Way, containing at least 1 trillion stars. And as astronomers probed deeper, an unsettling fact emerged. This colossal neighbor was not static. It was moving toward us. Spectroscopic measurements revealed a blue shift in Andromeda's light. Every spectral line, instead of being stretched toward the red as in most distant galaxies, was shifted toward the blue. This meant one thing. Andromeda was approaching at roughly 110 kilometers per second, over 240,000 miles per hour. A cosmic collision was inevitable. The idea was both thrilling and terrifying. In 4 to 5 billion years, the Milky Way and Andromeda would meet in a slow, gravitational embrace. The galaxies would not crash like solid objects. The distances between stars are too vast, but their mutual gravity would stretch, twist, and merge them into a new elliptical galaxy. Stars would be thrown into new orbits. Some solar systems would be cast adrift into the intergalactic void. Others might be pulled closer to the newly formed galactic core. The sun, if it still burns, will see its night sky transformed, arcs of blazing stars and tidal streams filling the darkness. The shock did not end there. As radio astronomy and high-resolution imaging advanced, Andromeda revealed structural oddities. At its center lay not one, but 2 bright nuclei, a double heart. This was not an artifact of imaging. It was real. The leading hypothesis suggested that one of the nuclei was the actual location of its supermassive black hole, while the other was a dense cluster of stars in orbit around it. The likely cause, a merger with another galaxy in the distant past, whose core had survived and now circled the central singularity like a ghost. In other words, Andromeda itself had been shaped by cosmic violence. Measurements of stellar motions and rotation curves brought another surprise, one that would shake physics to its foundations. The stars in Andromeda's outer spiral arms were moving far faster than they should be if only visible matter were exerting gravity. According to Newtonian mechanics, their speed should decrease with distance from the galactic center. Much like planets in the solar system orbit more slowly the farther they are from the sun. Instead, their speeds remained constant, a sign that some invisible mass was holding the galaxy together. This was some of the earliest evidence for what would later be called dark matter, an unseen halo of mass extending far beyond the visible galaxy, outweighing the stars themselves several times over. Andromeda's halo turned out to be enormous, possibly stretching over 1,000,000 light-years in diameter. It likely overlapped with the Milky Way's own dark matter halo even now. This invisible connection between our galaxies suggested that their eventual collision was not merely a future event. In some sense, their outskirts were already touching. The galaxy's light also carried traces of its ancient past. Spectroscopy revealed stellar populations of wildly different ages, from hot, young blue giants born just tens of millions of years ago, to ancient red stars more than 10 billion years old. Among these were metal-poor stars, stars whose composition suggested they formed before the universe had been enriched by generations of supernova. Some of these ancient stars were likely born in smaller galaxies that Andromeda had consumed long ago. Indeed, tidal streams of stars and faint arcs of light in Andromeda's halo revealed its history as a galactic predator. Over billions of years, it had torn apart and absorbed countless dwarf galaxies, leaving behind stellar fossils, elongated ribbons of stars tracing the paths of ancient victims. The galaxy's size and structure were not products of slow, isolated growth, but of repeated cosmic conquest to astronomers of the mid-20th century. Andromeda had transformed from a faint curiosity into something far more unsettling, a colossal, dynamic organism in constant evolution. It was not an island of serene starlight, but a predator, a merger, a harbinger of our galaxy's own fate. And yet, the more scientists learned, the stranger the picture became. High-energy X-ray observations revealed unexpected sources near its core, emissions that hinted at periods of intense activity in the past. Some researchers proposed that Andromeda might once have been a quasar, a galaxy whose central black hole blazed so brightly within falling matter that it could outshine all its stars combined. If true, the supermassive black hole at Andromeda's center, now relatively quiet, had once been a cosmic lighthouse visible across much of the observable universe by the dawn of the 21st century. The narrative was clear. Andromeda was not a static neighbor, but a force in motion, ancient, massive, and destined to change the shape of the night sky. It had become, in the minds of astronomers and philosophers alike, a mirror, a reminder that galaxies are not eternal structures, but fleeting arrangements of matter in the endless reshuffling of cosmic time. Even the Milky Way, the cradle of Earth, the framework of every human story, would one day be gone, its spiral arms dissolved into the new form born from its union with Andromeda. The scientific shock was not only in the data, in the velocities, the masses, the spectral lines. It was in the scale of perspective it demanded. The faint cloud noted by Al-Sufi, the mysterious nebula catalogued by Marius, the spiral measured by Hubble. All of it was part of a single realization, that we are part of a universe in motion, where even the grandest structures are subject to change. In Andromeda's blue-shifted light, scientists read not just a velocity, but a prophecy. It spoke of futures written on scales no human will see, yet which are already unfolding. A reminder that discovery is rarely the end of a mystery. More often, it is the beginning of a deeper one. By the dawn of the space age, Andromeda was no longer just a faint smudge on the autumn horizon. It had become a laboratory suspended in the dark, a cosmic mirror where humanity could test the laws of nature on a galactic scale. But to truly know it, astronomers would have to peel back its light, layer by layer, seeing not just what the clearly know it. Astronomers would have to peel back its light, layer by layer, seeing not just what the human eye could capture, but what the universe was willing to reveal across every wavelength it possessed. The optical view, elegant, spiraled, majestic, was only the first veil. With telescopes like Mount Palomar and later the Hubble Space Telescope, astronomers mapped the symmetry of its arms, traced the pearl-like chains of globular clusters, and charted the quiet elegance of its stellar disk. But beauty in visible light was a kind of deception. It hid as much as it revealed. Infrared surveys, from ground-based observatories to the Spitzer Space Telescope, reached deeper, slicing through the veils of interstellar dust. They exposed entire populations of stars invisible to the naked eye. Ancient red giants whispering the history of the galaxy's formation, and newborn suns still wrapped in their natal cocoons. These wavelengths revealed that Andromeda's structure was laced with unexpected currents of star formation, even alarmingly close to its central regions, activity thought to be rare in galaxies of its kind and age. Radio astronomy opened another frontier. Instruments like the Very Large Array in New Mexico detected the diffuse glow of neutral hydrogen gas stretching far beyond Andromeda's visible limits. These maps betrayed the presence of immense, hidden arms of material, tidal remnants of long-forgotten collisions, some arching tens of thousands of light-years into intergalactic space. Embedded within this sea of hydrogen were dozens of satellite galaxies, some no larger than cosmic embers, silently orbiting within Andromeda's gravitational grasp. These small companions, once invisible to optical surveys, became vital tracers of an even more elusive presence. The vast, ghostly halo of dark matter surrounding the galaxy. The halo's reach is staggering, spanning more than 1,000,000 light-years, overlapping with the outer edges of our own Milky Way's dark matter envelope. Its mass, invisible yet undeniable, outweighs the combined light of billions of stars. And yet its nature remains hidden, a shadow written into the mathematics of galactic motion. By tracking the orbits of satellite galaxies and the velocity of gas far from the core, scientists refined their models, suggesting that dark matter accounts for more than 90% of Andromeda's total mass. But the most formidable discovery lay at the galaxy's heart: high-resolution imaging and stellar motion. Studies revealed that Andromeda, like the Milky Way, harbors a supermassive black hole at its core. Mass estimates place it at nearly 100 million times the mass of the Sun, significantly larger than Sagittarius A*, the black hole at the center of our own galaxy. The dynamics of nearby stars, whipping around at dizzying speeds, betray the black hole's invisible grip. X-ray telescopes like Chandra detect bursts of high-energy radiation from matter spiraling inward, occasionally flaring when the black hole feasts on a passing star or cloud of gas. These X-ray observations also uncovered a realm of violence hidden beneath Andromeda's serene optical portrait: clusters of neutron stars, stellar mass black holes, and the turbulent remains of ancient supernova. The galaxy's inner regions are stitched together by dust lanes, dark rivers of carbon and silicate grains drifting through the light. These rivers are not lifeless. Within them, pockets of cold gas collapse under their own weight, igniting new stars even in the galaxy's bustling core, where such creation should be rare. In the ultraviolet, the Galaxy Evolution Explorer traced streams of young, hot stars shimmering along the spiral arms, their light blazing at temperatures tens of thousands of degrees hotter than our Sun. Combined with infrared maps, these ultraviolet observations told a story of cycles, matter collapsing into stars, stars shedding their outer layers, and heavy elements seeding the next generation. Andromeda, for all its age, is not a relic. It is alive with quiet, persistent creation. By stitching together these observations across the spectrum, astronomers have built a portrait far richer than the one Hubble himself could have imagined a century ago. Andromeda is no longer a distant island of light. It is a layered world, a spinning cathedral of stars, dust, gas, and dark matter, every component moving to rhythms written billions of years before Earth existed. Yet with every detail resolved, new mysteries emerge. Why do certain star-forming regions defy their predicted lifespans? What ancient galactic mergers left faint scars in its hydrogen arms? Could the immense dark matter halo be evidence not just of unseen particles, but of a deeper, stranger framework of gravity itself? Science now stands in the middle of the map it has drawn, aware that each wavelength is both a revelation and a veil, that the heart of Andromeda, even when measured, charted, and imaged in exquisite detail, still hums with unanswered questions. For centuries, the Andromeda galaxy seemed a model of cosmic order, a grand spiral, poised and balanced, its arms unfurling in silent symmetry. Yet the deeper science looked, the more that symmetry began to fracture. Beneath the veil of starlight, Andromeda harbors scars, irregularities, and patterns that whisper of a far more turbulent past. The first rupture in this image came with the discovery of its strange double nucleus. High-resolution imaging from the Hubble Space Telescope revealed not one, but two bright concentrations of stars at its heart, locked in a gravitational dance mere light years apart. To the untrained eye, they appear as twin lanterns burning in the dark. To astronomers, they are a riddle, possible relics of a galactic collision, where a smaller galaxy was not merely consumed, but woven into the very core of Andromeda. The stars between these two centers trace orbits that twist and warp, hinting that the central black hole has not always ruled alone. Far from the core, in the faint halo that extends hundreds of thousands of light years, the mystery deepens. Here, the motions of stars refuse to obey predictions. Some streams of ancient suns move in elongated paths, as if pulled by invisible currents not accounted for by standard dark matter models. These anomalies raise unsettling questions. Is the shape of Andromeda's dark halo stranger than we imagine? Or could our understanding of gravity itself be incomplete? In the quiet data of stellar velocities, some physicists see the faint outline of new physics waiting to emerge. Closer to the heart, the supermassive black hole minus 100 million solar masses of compressed spacetime show signs of a restless past. Archival X-ray and radio observations suggest cycles of activity where the core once blazed as a quasar, flooding interstellar space with radiation powerful enough to alter the galaxy's evolution. For now, the black hole lies in a relatively quiescent phase, its accretion disk dim, its jets silent. But the record written in surrounding gas clouds implies that this calm is temporary, that the heart of Andromeda has throbbed with far greater violence before, and could awaken again. The stellar population itself tells a story no less complex. Among Andromeda's billions of stars, astronomers have found populations with a startling lack of heavy elements, metal-poor stars whose chemistry belongs to a much earlier epoch of the universe. These are not the children of Andromeda's own spiral arms, but likely refugees, fragments of ancient galaxies torn apart and assimilated over billions of years. They move in coherent streams, ghostly remnants of cosmic cannibalism, still carrying the elemental fingerprint of their original homes. Every one of these discoveries carries a shadow, the future. For in 4 billion years, the Milky Way and Andromeda are destined to collide. The approach is already measurable, a mutual drift of roughly 110 kilometers per second, silent across the void. Simulations predict that the spirals will tangle, arms torn into tidal streams stretching hundreds of thousands of light years. Stars will be thrown into intergalactic space, while others will fall inward toward the merged heart, where the two central black holes will spiral together in a cataclysm of gravitational waves. For solar systems caught in this ballet, the consequences will vary. Most will survive intact, flung into new orbits around the merged galaxy's core. But the night sky will be rewritten. Over millions of years, Andromeda will swell from a faint smudge to a looming disk that dominates the heavens, its structure, fracturing, its light braided with our own. When the collision settles, the two spirals will be gone, replaced by a giant elliptical galaxy, smooth, round, and filled with the faded light of ancient stars. And yet, even this cosmic union will not erase the questions that Andromeda poses now. The double nucleus, the disobedient halo stars, the whispers of a quasar past. These are not just historical curiosities. They are pieces of a larger, hidden architecture of the universe, one that still evades human comprehension. The escalation is not in the violence we expect from the coming collision, but in the realization that the galaxy next door, the one we can see in such exquisite detail, refuses to yield a simple truth. It is a reminder that the closer we look at the cosmos, the more it begins to look back with questions of its own. Every mystery demands an answer. Yet in astronomy, answers are rarely singular. They arrive as constellations of possibility, glowing faintly against the unknown. In the case of Andromeda, each anomaly, from the restless double nucleus to the strange velocities in its halo, has given rise to theories that seek to bind them together in a coherent story. Some remain grounded in the established pillars of astrophysics. Others push into the frontier, where the edges of known science begin to dissolve. The most enduring framework begins with an unseen substance, dark matter. Astronomers believe that Andromeda, like all massive galaxies, is embedded in a vast halo of this invisible material. It neither emits nor absorbs light, yet its gravitational influence sculpts the motions of stars and gas. According to the standard model, dark matter outweighs ordinary matter by a factor of 5. Its halo should be roughly spherical, extending far beyond the galaxy's luminous arms. Gravitational lensing, the bending of light from background galaxies by Andromedas mass, has been used to map this hidden architecture. These measurements largely confirm the halo's presence, but they also hint at irregularities, clumps, asymmetries, and extended streams that suggest Andromeda's dark matter has been stirred by past collisions. Such interactions could explain why certain halo stars trace peculiar elongated orbits as if pulled by invisible rivers in the dark. Yet the deviations are persistent enough that some researchers wonder if our theory of dark matter itself might need revision, or if gravity, on cosmic scales, behaves in ways Einstein never imagined. From there, the narrative of galactic cannibalism unfolds. In this theory, Andromeda's mass and complexity are the result of billions of years spent devouring smaller galaxies. Astronomers have traced faint tidal streams, long ghostly ribbons of stars that arc far from the main disk. These are the shredded remnants of past companions, still following the trajectories they took before being subsumed. The metal-poor star populations found deep within Andromeda's halo are relics of this process, each one a fossil from a world long gone. Computer simulations support the idea that major mergers have shaped Andromeda's very core. The double nucleus could be the lingering footprint of a galaxy nearly the size of the large Magellanic Cloud, swallowed in a violent union that displaced the central stars and altered the supermassive black hole's domain. Such events would send ripples through the dark matter halo, distort the spiral arms, and trigger bursts of star formation, patterns still visible in the blue clusters scattered near its outskirts. This leads to another, More speculative hypothesis. Supermassive black hole binaries. If Andromeda has indeed merged with other large galaxies, each would have brought its own central black hole. For a time, perhaps millions of years, both could orbit one another within the galactic nucleus. Such binaries would emit gravitational waves on colossal scales, subtly altering the orbits of nearby stars and possibly accounting for the strange stellar motions near the double core. Detecting such a pair directly remains beyond current capabilities. Yet planned observatories, like the Laser Interferometer Space Antenna, LISA, could one day confirm whether Andromeda still hides two supermassive hearts beyond the gravitational and structural puzzles. There are questions that drift into the realm of life itself. Andromeda contains hundreds of billions of stars, many with planetary systems. Statistical models, based on exoplanet surveys from missions like Kepler and TESS, suggest that within this galaxy, there could be billions of Earth-like worlds. Planets in the habitable zones of their stars, where liquid water might persist. The light from these worlds has not yet reached us in detail, fine enough to reveal atmospheres, oceans, or civilizations. The distance, 2.5 million light-years, ensures that if signals exist, they would be echoes from a time before our species evolved. Some astrobiologists speculate that if intelligent life has arisen in Andromeda, it could have experienced cycles of growth and collapse on timescales that dwarf human history. Entire civilizations might have risen to cosmic awareness, charted the spiral arms of their home galaxy, and vanished before Earth itself cooled enough for life to begin. Their monuments, if any survived, would now be dust mingled with the interstellar medium, awaiting incorporation into future worlds. Even more provocatively, there is the question of cosmic isolation. The vast gap between our galaxies is not empty, but filled with tenuous gas and dark matter, an ocean across which interstellar craft would require millions of years to travel. In this light, Andromeda's civilizations, if they exist, are like distant lighthouses whose beams cannot yet cut through the fog. This separation is not only physical but temporal. What we see of them, they see of us, is locked in the ancient past. Two galaxies, two stories, unfolding in parallel, unaware of their shared future collision. Theories, however elegant, remain provisional. Andromeda refuses to be reduced to a single equation, a single model. Each layer of observation peels back to reveal another complexity, another anomaly that demands both humility and imagination. It is possible that the strange motions in the halo will eventually yield to more refined dark matter maps, that the double nucleus will resolve into a comprehensible relic of a past merger. It is equally possible that some features will persist as riddles until technology and theory evolve far beyond our present state. For now, the galaxy remains both an open book and an unreadable manuscript. The laws of physics we apply to it are the same ones we use to understand our own Milky Way, yet Andromeda answers with a different accent, a different rhythm. In its shape, in its hidden matter, in the invisible lives that may orbit its distant suns, it holds not only the history of the universe, but also the blueprint for the universe to come in the end. Speculation is not idle dreaming. It is the scaffolding upon which tomorrow's discoveries will be built. And in the quiet spaces between fact and possibility, Andromeda waits, patient as the night, for us to close the gap between what is known and what is only imagined. The universe does not give up its secrets willingly. To study a galaxy 2.5 million light-years away is to work at the limits of light itself, to coax faint photons across cosmic gulfs, and to translate them into meaning. Andromeda, with its sprawling spiral arms and hidden depths, demands not one instrument, but an armada of them, each tuned to a different frequency of the cosmos. In low Earth orbit, The Hubble Space Telescope still drifts silently above the atmosphere. Its mirror is fixed on the heart of Andromeda. It was Hubble's deep field observations that first resolved individual stars in another galaxy, breaking the blur into millions of points of light. These are not just stars, but markers in a vast celestial map. Their colors, luminosities, and rhythms revealing the ages and histories of Andromeda's stellar populations. Kifide variables, novae, and red giants all become distance markers, anchoring the galaxy in the cosmic web with unprecedented precision. Farther into the infrared, the James Webb Space Telescope peers through veils of dust that obscure Andromeda's inner lanes. Its sensors reveal cold star-forming nurseries that optical light cannot penetrate, clouds where gravity gathers raw hydrogen into the first sparks of new suns. Here, Webb detects the chemical fingerprints of these regions, tracing not just the formation of stars, but the complex cycles of matter that may one day give rise to planets and, perhaps, life. Meanwhile, the Gaia spacecraft, operating from a stable point beyond the moon's pull, measures the positions and motions of stars across Andromeda's expanse. Over years, its exquisitely precise astrometry builds a living model of the galaxy's dynamics, how each star arcs through space, how streams of ancient collisions still ripple through the halo. This data reveals patterns invisible to the eye, the faint tidal remnants of galaxies long since consumed, the signature of Andromeda's gravitational pull on its satellites, and the inevitable drift toward our own Milky Way. From the ground, the work continues. High atop Mauna Kea, the twin domes of the Keck Observatory open their segmented mirrors to the night, using adaptive optics to counteract the blur of Earth's atmosphere. Keck spectrographs dissect Andromeda's light into its component wavelengths. Each spectral line tells a story: the velocity of a star, the composition of a gas cloud, the rotational speed of the spiral arms. In the Chilean desert, the Very Large Telescope, VLT, joins this effort, mapping the kinematics of Andromeda's core and searching for subtle shifts that might betray the influence of its supermassive black hole dot beyond the optical spectrum. The Atacama Large Millimeter Submillimeter Array, ALMA, sweeps the galaxy in radio waves. ALMA's vision is tuned to the cold molecular gas that fuels new star formation. By charting these flows, astronomers can see how matter moves inward, feeding the central regions, and how past interactions with smaller galaxies may have stirred this cosmic weather. These observations also track the long dark lanes of dust that thread across Andromeda's disk, absorbing light yet glowing faintly in the millimeter band. But observation is only half the battle. To predict Andromeda's future and ours, scientists turn to the realm of simulation. On supercomputers capable of trillions of calculations per second, they recreate the galaxy in silico. Every star, every cloud of gas, every invisible halo of dark matter modeled in three-dimensional detail. These simulations are run forward in time, watching as Andromeda and the Milky Way draw closer, their halos overlapping, their shapes distorting under mutual gravity. In the most detailed models, the two spiral galaxies pass through one another in a slow rainbow, merging over billions of years into a single elliptical giant. Stars are flung into long arcs, planetary systems are displaced, and the central black holes spiral inward until they unite, releasing gravitational waves that roll across the universe. The simulations are not just dramatic forecasts. They are tools to compare against present-day observations. If a model predicts a particular stream of halo stars or a subtle warp in Andromeda's disk, astronomers can search for that feature in Gaia's data or Keck's spectra. In this way, the present becomes a puzzle piece in a story that stretches both backward into Andromeda's past and forward into its ultimate fate. Looking further ahead, some envision a day when our study of Andromeda will no longer rely solely on telescopes confined to Earth's neighborhood. Concepts have been proposed for deep intergalactic probes, autonomous craft propelled by solar sails or fusion drives, capable of traveling far beyond the Milky Way's edge. Such missions might carry telescopic arrays into the void between galaxies, reducing the glare of our own stars and giving an unobstructed view of Andromeda's structure. In the realm of the speculative, there is even talk of gravitational lens telescopes stationed near the Sun's focal point, using the Sun's own gravity to magnify distant targets like Andromeda by orders of magnitude. For now, these remain dreams, blueprints for a future when human technology has advanced enough to cross the cold gulfs of intergalactic space. Until then, the armory of instruments already in our hands continues to refine, sharpen, and deepen the image of our approaching neighbor. The study of Andromeda is not a single project, nor the work of a single generation. It is a tapestry woven across decades, each instrument adding its own thread of detail. The Hubble Space Telescope may one day fall silent, the James Webb may fade, but the legacy of their data will endure, carried forward by new tools and new minds. The quest is unending, because the galaxy itself is unending, a moving target, in space and in time. And so the watchers on Earth and in orbit continue their vigil. Each photon they capture a messenger from the past, each dataset a window into the future. The science is precise, the measurements exact, but beneath it all lies something older than equations. The simple, enduring need to know what waits for us in the dark, between the stars. In the silence of space, there are no footsteps. There are no ships skimming the void between galaxies. Yet the journey is real. It is made not with motion, but with light. For more than a century, humanity has reached toward Andromeda without ever leaving its own cradle. The voyage has been a patient unraveling of photons that have traveled for 2.5 million years, carrying within them a memory of where they began. Each one is a silent envoy, crossing an ocean that no human eye will ever directly see, until it falls into the open hand of a telescope on Earth. In this way, we have traveled the breadth of the local group without moving a step. We have mapped the contours of another galaxy, traced the birthplaces of its stars, weighed the mass of the black hole that anchors it, and glimpsed the restless winds of its interstellar clouds. We have done all of this not by touching Andromeda, but by listening to its light. And yet, even as we study it from afar, Andromeda is not a stranger to our destiny. Its slow approach is written into the fabric of space-time itself. Two spirals, separated by a gulf of nearly 3 million light-years, are locked in a gravitational embrace. Across that abyss, the pull is relentless. It is a dance choreographed over billions of years, each partner tracing an arc that leads inexorably to the other. The meeting will not be swift. Long before it happens, the continents on Earth will have shifted beyond recognition. The oceans will have changed their shapes. Stars that now guide navigators will have vanished or been replaced by new constellations. Yet through all these transformations, the trajectory will remain unbroken. The two galaxies will continue to draw closer, the spiral arms of each beginning to distort in anticipation of the union to come. In the scale of human life, the event is impossibly far away. But in the scale of the cosmos, it is already underway. The first stirrings of tidal distortion are visible in the motions of Andromeda's outer halo. The invisible tendrils of dark matter have already intertwined. The future collision is not a distant possibility. It is a process already begun. Its opening chapter written in the drifting of stars. There is a paradox here. Andromeda's heart, though unimaginably distant, is already part of our future. The stars that circle its core today will one day shine in the same sky as the remnants of our own sun. Planets now orbiting in the outskirts of Andromeda may, billions, of years from now pass through the merged star fields of the Milky Way Andromeda galaxy. Somewhere, a world may watch our descendant stars rise. This inevitability forces a quiet reckoning. Humanity's presence is so brief against such a backdrop that even the most enduring monuments, the longest civilizations, and the most persistent cultures will vanish long before the galaxies meet. In cosmic terms, we are a flicker, a spark in the dark, here, then gone. But perhaps that brevity is part of the beauty. The very act of knowing what is to come, of understanding that we live within a much longer story, gives our moment a kind of significance it would not otherwise have. For in the universe, nothing truly stands still. Every particle drifts, every star moves, every galaxy falls toward another. The great cosmic web is not frozen in place, but alive with motion. Even in the coldest regions of intergalactic space, the dance continues. And we, for all our fragility, are participants in it. To gaze upon Andromeda is to see the future written in light. It is to witness not just a galaxy, but a destination. Somewhere within its spirals, in some epoch we cannot reach, our own stars will join its swarms. And whether or not life endures to see that day, the fact remains. The heart of Andromeda is already part of our path. We are bound to it, as surely as the moon is bound to Earth, or the Earth to the sun. That bond is invisible, carried not by chains, but by the gentle, relentless pull of gravity, a force that acts without sound, without haste, and without mercy. The story of Andromeda and the Milky Way is not one of conquest, but of union. It will be violent in its detail. Stars flung into the deep, gas clouds compressed into furious bursts of new suns. But in the end, the two galaxies will become one. Their shapes will dissolve, their histories will merge, and a new galaxy will rise in their place.